All right, hello pre-calc students. We'll be covering section 2.5, part 1 today, which is complex zeros. In this part, we're mostly going to be looking at zeros and putting polynomials together from known zeros and factors. And then in part 2, when we come back next class, we will be doing the opposite. We'll be looking at polynomials and pulling them apart by factoring and finding zeros from them. Today we'll be covering a couple of important theorems, the first of which is the fundamental theorem of algebra. It states that a polynomial function of degree n has n complex zeros. The zeros might be real or non-real, and some of those zeros may be repeated. In other words, the number of zeros that you're going to see for a polynomial, both real and imaginary zeros, matches the degree of the polynomial, and some zeros may be repeated. So if I had a polynomial function that was, say, a 5th degree polynomial, say its lead term was 2x to the 5th power, then I would know that since this is a 5th degree polynomial, that I should be seeing 5 zeros. Those zeros might be real, they might be complex, and it's potential that there could be some repetition. Another important theorem is the complex conjugates zeros theorem. And this states that it states that all zeros for a polynomial, all complex zeros for a polynomial come in conjugate pairs. So if I know that a plus bi is a zero of a polynomial, then a minus bi must also be a zero. So if for some reason I knew that 2 minus 7i was a zero of a particular polynomial, then 2 plus 7i must also be a zero. So anytime you have one complex zero, you automatically are going to have another one, and that other one's going to be the original one's complex conjugate. All right, a couple interesting things come out of this. Looking back at the previous example, if I had a 5th degree polynomial, I know that I have 5 zeros. I also know something about those zeros. I know that at least one of these zeros must be a real zero. I want you to think about that for a moment and see if you can figure out how I know that. If I know that I have 5 zeros, I know that at least one of those zeros must be a real zero. How did I know that? I know that there are 5 zeros. What I also know is that if this zero right here is a complex zero, then one of the other ones has to be also, because they always come in complex conjugate pairs. So if one of these is a complex zero, then another one has to be. I could have potentially another set of complex zeros, but there's no way that my last one could also be a complex zero because there's no one for it to pair up with. So if all of these other 4 are complex zeros, then this one has to be a real zero, because the theorem says if it's a complex zero, it must have a conjugate pair, and there's just not enough zeros for us to do that. All right, that's going to become useful when we get into taking zeros apart when we meet again next time. So let's use these theorems and do some problems. And just so you know, these problems mirror the instructions and types of problems that you're going to see in your assignment for today. So in this first example, they've given us a function. It's a polynomial function, but it's in linear factorization form. They want us to write the polynomial in standard form, identify the zeros and the x-intercepts of its graph. So let's do the easy part first, which is identifying the zeros. So what do I know by looking at this? And actually, there's a typo here. Let me fix this. This does not match what you see on your screen. Sorry, this doesn't match what you see on your paper. Yours says -3 here. All right, so what do I know? Well, this factor is going to give me a 0, and it's going to give me a real 0 at -2. And this factor is also going to give me a 0, a real 0 at +3. This factor is going to give me a complex 0 at -√5i. And this factor will also give me a complex 0, this one at +√5i. The instructions also asked us for x-intercepts. So we'll get x-intercepts from any zeros that are real only. So these two are complex zeros. They will not contribute x-intercepts. We do have an x-intercept from that real 0 at -2, 0. And another one from the 0 at 3. That would be 3, 0. All right, so we've taken care of finding the zeros and the x-intercepts. The more challenging part is going to be to write the polynomial in standard form. So basically, I need to go through and multiply all these factors out. Now, there are a couple things that are going to help us do this, some shortcuts that could make this potentially a little quicker for us. One of the shortcuts, since we're dealing with complex conjugates here, would be the complex conjugate shortcut, which is that a plus bi times a minus bi is equal to a squared plus b squared. So I am going to do that to multiply out these two factors. So those are complex conjugates, so we should be able to apply this shortcut here. So when we multiply them together, our a is just an x here, so we square that. My b is √5. So we square √5 and we get 5, and the shortcut tells us to put a plus in between, so x squared plus 5. All right, I'm going to go ahead and multiply these two factors in front together. Might as well do that in the same step. And for that, we just need to do a FOIL, or however you want to do that. Several different ways to do it. I'm going to work through it mentally in my head. I've got x times x is x squared. My trailing term will be +2 times -3, that's -6. And I also have a 2x and a x times -3 is -3x. 2x minus 3x is -1x. If you prefer to do that by drawing a box or writing out the whole FOIL thing, you can do it that way. It takes a little bit longer, but you're going to get to the same thing. All right. So here is a slightly less factored version of our polynomial, but it's still not in standard form. To put it in final standard form, I am going to need to multiply these two factors together. And again, choose your method for doing this. I personally prefer to make a table. It keeps me more organized. I've got x squared -x -6. So I'll be multiplying by x squared plus 5. X to the 4th, -x to the 3rd. I'll put a 1 there. -6x squared. Here I've got a 5x squared, a -5x, and a -30. I do have some like terms I can combine there, so I'll just go straight to my final answer here. And I'll underline as I use them. So x to the 4th doesn't combine with anybody, neither does -1x to the 3rd. -6x squared and +5x squared, that's going to be -1x squared. -5x doesn't combine, and neither does -30. I've picked up everything, so that's going to be my final polynomial in standard form. All right, now we've seen a lot of ways that we can check work. Unfortunately, this gets a little bit tougher to do when we start introducing imaginary values. So how I would have checked this without these imaginary values is I could try and graph this factored form and then graph my final form and see if those graphs match. That's not going to work out so well for us, but what I can do instead, I can check and make sure Now I'm going to go ahead and put these two factors. I only got x plus 2 and x minus 3. We can't graph things that have i's in them, but I could, instead of having these two separate factors, I could have what we got when we multiplied them out, which is x squared plus 5. Now I'm making an assumption that x squared plus 5 is correct. And hopefully it is, so I might want to go back and double check that work. But I can check all of the other work now by typing in my final format. So give me a moment to do that. Double checking, make sure I've got everything typed in correctly. And what I want to do is graph these and make sure they match. I actually prefer to look at the table because it's really easy to quickly check and make sure that I'm getting the same y values for everything in the table, and that totally matches up. So I'm feeling confident that at least I did this step correctly and I did from here to here correctly. The only thing I'm not 100% sure on is if I got x squared plus 5 if this part's correct, so I would just want to go back and double check my work for that. All right, let's move on. Example 2 is kind of similar, but they didn't give us any factors this time. They're just giving us some zeros. So our goal is to write a polynomial in standard form. So we're going to need to start by writing factors, and then we'll need to multiply those factors out. So very similar to the last one, except they didn't give us the factors. In the book, I think it says of minimum degree also in the instructions. So here's the thing. They told me that we have a 0, -2, and 1, and that's fine, but they gave us a complex 0 here. And I know, because of the complex conjugate zeros theorem, I know that if 2 plus I is a 0, then that must mean that 2 minus I must also be a 0. So even though they only gave us 3 zeros, I know that there have to be 4. So we're going to go ahead and write down our 4 factors, and then we'll just need to multiply those out. So my 4 factors are going to be x plus 2, x minus 1, x minus 2 minus I, and x minus 2 plus I. And now I just need to do the tedious work of multiplying these things out. All right. So the trickier piece is going to be these last two. There are some shortcuts for doing this. And I can show you a couple of those shortcuts here. Your long way of doing it would be to multiply them out using some kind of table or method like that. You've got x minus 2 minus I and x minus 2 plus I. You're going to end up with a 3x3 table with lots of terms, 9 terms altogether. A bunch of them are going to cancel out, but that will work. If you're comfortable, though, you could treat this as a conjugate pair because it is a conjugate pair. Here's what I would do if I were going to try and use a shortcut on this. Okay, so I would remember a couple of shortcuts. One is that a plus bi times a minus bi is equal to a squared plus b squared. The other one is that a plus b quantity squared is equal to a squared plus 2ab plus b squared. Let me show you how I'm going to use these two shortcuts. When I look at these two factors, I'm going to treat this as my a because it's the same in both. And then my b value is actually going to be a 1. So when I multiply these two factors together, the shortcut says that I'm going to have a squared plus b squared. Well, a squared is just x minus 2 squared. That's what a is. And then plus, and then b squared is just going to be 1 squared. Okay. So I grouped the x and the -2 together to be my a part, and then the b would have been 1. It's the coefficient on the I. A squared is the x minus 2, quantity squared, and then 1 squared. That's using this shortcut up here. Now I can do the x minus 2 quantity squared using another shortcut. X minus 2 quantity squared using this shortcut would be x squared minus 2 times a times b. That'd be 2 times x times -2, or negative 4x, and then plus b squared. So plus -2 squared is 4. And I still have this 1. All right, so those two factors come together to give us x squared minus 4x, and then combine like terms here, we have plus 5. X squared plus minus 4x plus 5. All right, these two terms are going to multiply together. And then again, use FOIL or a table, however you want to do it. X squared, 2 times -1 is -2. I've got a 2x and a -1x. So it's going to give me positive 1x. All right, and now comes the real tedious part, and that's multiplying those two trinomials together. I'm going to do my work off to this side over here where I've got a little bit of space to do that. So I've got x squared plus x minus 2 for one, and then x squared minus 4x plus 5 for my other, and I'm just going to need to go through and multiply. I'll probably go back and do a quick double check because there's lots of room for error here. I just found one. This is tedious. Not terribly difficult though. Positive. Okay, feeling pretty good there. And then we'll look for some like terms that we can combine together here as we write our final polynomial. So I have an x to the 4th. That doesn't combine with anybody. I've got a -4x to the 3rd and an x to the 3rd. That's -3x to the 3rd. We have 3 terms with x squareds in them. So 5 minus 4 gets us 1, minus 2 gets us -1. So -1x squared. 5x and an 8x is 13x. And then a minus 10 at the end to finish it off. And we've used everything. And there's our final polynomial. How am I going to check this? Again, it's difficult to check completely, but I could type the polynomial in and make sure that I do see intercepts at -2 and 1. That would make me feel pretty good about it. Should also see some wiggles in the polynomial from those, or the polynomial graph from those imaginary zeros as well. Let me just type this in really quickly. Okay, so I'm looking for x-intercepts at -2 and 1. They should be singles. There's -2, there's 1. We got some wiggles in there. Feeling pretty confident. Okay, moving right along, this will be our final example. This is a lot like the last one, except this time they're giving us multiplicity for our zeros. They only gave us 2 zeros, but one of them is complex, which means that there has to have a conjugate pair. So if 3 plus 2i is a 0, then 3 minus 2i is also a 0. They also gave us 3, but they gave us a multiplicity of 2. So as we go to write out our factored forms, we're going to have x minus 3. It's going to be squared because of that multiplicity of 2. we're going to have an x minus 3 minus 2i from the 0 that they gave us here. And then its complex conjugate pair buddy would be x minus 3 plus 2i. So I'll be using some similar tricks to how we did in the last one to make this process a little bit easier for me. In this one, when I do my complex conjugate pairs, I'm going to think of A as x minus 3 and B as 2. So the shortcut for multiplying those two complex conjugate pairs together is a squared plus b squared. So I got x minus 3 squared plus b squared would be 2 squared. I'll use my shortcut for x minus 3 squared. The quantity x minus 3 squared, that's going to be x squared minus multiply them together and double it, which would be 6x. And then we'd have plus 9. And then don't forget about our plus 2 squared, that's a 4. So that factor is x squared minus 6x plus 13. They also gave us the x minus 3 squared. So we'll go ahead and multiply out x minus 3 times x minus 3. Again, I'm going to use my shortcut here. It's a binomial squared, so square the first thing, multiply them together and double it will give me minus 6x. Square the last gives me that plus 9. And now I just need to multiply those two trinomials together to get my final form in standard form. So I'll be making a box again. The other reason I like making this rectangle or table, however you want to think of it, like you saw in the last example, your like terms tend to line up on a diagonal a lot of times when you do these. So it makes the combining like term part at the end a little bit easier also. It's going to turn positive. Um, 13 times 6 I should be able to do in my head, but I'm not trusting myself today. And 13 times 9 is 117. And yes, I did use my calculator there too. Let's do a quick check here. It's so easy to make one small mistake here and throw the whole thing off. That's positive, good, that's negative. Positive, negative, positive. 13 times 6, 78, yes. Okay, I think I'm good. So what do we got? We got x to the 4th. Got minus 12x to the 3rd. We're gonna have a few x to the seconds. 9 and 36 is 45. We need 58x squareds. Negative 54 and negative 78 is negative 132 x's. And then we got our 117. All right, I'm going to go ahead and graph this and see what I see. I know that I should be seeing an x-intercept at 3 and that my graph should be bouncing off at that x-intercept. So let's see if that works out for us here. Yep, and there we go, bouncing off at 3. That makes me feel fairly confident. All right, so you've basically got 3 sections of problems for your assignment. The examples that we did mirror these set of problems. In addition, you're going to be doing some problems from 2.4. For 53 and 54, these are the ones that you should be doing by hand. So don't forget, you're looking to graph You're going to find zeros from the graph, from your x-intercepts. And sometimes you're going to be using a P over Q list to help you with that. If you have any other remaining zeros, you're going to be using synthetic division. And then once you get it down to a quadratic, then you'll be using your quadratic formula. Right. Thank you for your attention. Have a great day.